that are, it's a completely different, really completely new. The idea is really new. So let's see, we're in section 11.1. So what we're interested in with limits is we have some function and we want to know what that function gets close to as our independent variable, as x approaches some number. So for our idea of a limit is that our function f of x gets, and we're going to say arbitrarily close to L as x approaches C. And this idea of arbitrarily close, we'll say it in a lot of different ways. Arbitrarily close as you want. Very close. We will use a lot of words to say we can get as close as we want to this number L. You'll make in calculus, you'll make that idea, that definition more rigorous. The idea that as close, we'll come up with a definition of what we mean by close in calculus. We call L the limit of f as x approaches C. And our notation is the limit as x approaches C of f of x equals L. Couple of important things to remember as we talk about limits. What we're interested in with limits is we're interested in what f gets close to. We're not interested in what f equals at C. We want to know what it gets close to. So we'll say this over and over as we go through this. The limit is independent of the function value. We'll be dealing with functions that have a limit at a certain point, and the function's undefined at that point. So we don't have to have a function value at that point. So a lot of times, well, with nice functions, we can just plug numbers in and find our limits. But often we're interested in functions that don't behave nicely, but we're still interested in what the limit is. And one of the ideas behind calculus is we come up with a way, this idea of a limit, so we can essentially divide by 0. It's not exactly what we're doing, but that's kind of the process. So what we want to do today is look at this idea of a limit. How do we figure out what the limits of functions are, and how do we work with limits? And we'll talk about how we find limits of nice in quotes, nice functions. All right, so one of the easiest ways we can figure out a limit is by a table of values. So let's look at a table. So for example, we'll have a very nice function here. The limit as x approaches 4 of x minus 1. So we're just going to make a table of values. We're going to have x and f of x, and I'm just going to plug some numbers in and calculate. So here is our x equals 4, and I want to know what f of x gets close to as x gets close to 4. So we're going to come from both directions. We're going to come from less than 4, and we're going to come from greater than 4. So here is a number that's kind of close to 4, 3.9. And f of x, when we plug that in, we get 2.9. A little closer to 4, 3.99, and f equals 2.99. Let's go to the other side of 4. So 4.001. And f, when we plug that in, we get 3.001. And when f is 4.001, we get 3.01. And finally 4.1, 3.1. So looking at this table, what is f getting close to as x gets close to 4? 3. As x gets closer and closer to 4, f is getting closer and closer to 3. So we say the limit as x approaches 4 of x minus 1 equals 3. And notice for this function that f of 3, if I just plug, or sorry, f of 4, if I just plug that in, f of 4 equals 3. So this would be an example of a nice function that we can just plug a number into. They're not always nice. And usually the ones we're interested in are not nice. We have to do a little more work. So let's look at an example of one of those. And I'll remind you how to do these tables in your calculator. So let's look at the limit as x approaches 2 of x squared minus 4 over x minus 2. So for this function, f of 2 is undefined. Because I end up dividing by 0. That doesn't mean that the function doesn't have a limit. That doesn't mean that the function doesn't get close to something as x gets close to 2. So let's look at a table of values here. So here's what we're interested in. As x gets close to 2, what is my function getting close to? If I plug in 1.9, and I was nice and did all the calculations for you, I get 3.9. As f is 1.99, a little closer to 2, I get 3.99. 2.001 will go to the other side, and I get 4.001. And getting a little further away, 2.01, 4.01, and 2.1, and 4.1. So what does it look like from this table? What is f getting close to as x gets close to 2? 4. So we say the limit as x approaches 2 of this function, x squared minus 4 over x minus 2 equals 4. Even though the function is undefined at x equals 2. So we can have a limit even though our function is undefined. The function value is independent of the limit. The limit is independent of the function value. So let's have a reminder of how we do. Some of your homework problems will ask you to set up a table in your calculator to find your limit. So let's have a reminder how we do that. So we're going to do this problem and come up with this table. So the first thing you want to do is make sure you set up when you did your polar, or when you did your conics project, you turn the axes off. So I'm going to go here to second format and make sure your axes, you arrow down there and turn your axes back on. So it'll be set like this. You want to arrow over there. So you set your axes on. And you also want to make sure that in your mode you're set to graph functions and not polar. So if you still had it set to polar, make sure you're all set like this. Alright, so let's enter our function in there. Our function was x squared minus 4. And we were dividing that by x minus 2. And I'm going to go to the table. So before I go to the table, we're not going to graph this. We're going to go to I'm going to set up the table. I'm going to go second table set. And I'm changing this second number, this delta table, to 0.01 instead of 1 because we want a little more accuracy here. And I'm going to start my table at 1.96, so kind of close to 2. Then I'm going to go to my table, second table. Here are my x values. X is changing by 0.01, and as x gets close to 2, and x is 2, we get an error, but as x gets close to 2, on either side of 2, I can see that my function is getting closer and closer to 4. I get 3.99, 4.01. And if I wanted to zoom in a little more, I could do my table set and I could change this to 0.001. Whoops, not 4 zeros. Let me clear that. 0.001. There we go. And then if I go to my table now, I have even more. I probably should have started at 1.99. But we can see we're getting closer and closer. Whoops. Pressed too many. So now we're getting further away from 2. My computer can't keep up with my key presses. So as we get closer and closer to 2, on either side, the function is getting closer and closer and closer to 4. So that's how you would set up your table, and we can see that we're getting closer and closer to 4. And this is what our graph looks like. If I go to my graph, it looks like a line. What the graph doesn't show us is that at x equals 2, we have a hole in the function. So our function is getting closer to 4, even though our function is not defined at x equals 2. Yes?
Could you simplify the equation to x equals 2 when putting our lines into 2's lines?
So we'll talk about using algebraic techniques, doing that kind of thing next time. So we want to get the idea of the limit here, but then we'll start simplifying our functions and figuring out how we can figure out what the limit is without going to a table or without going to a graph. So that's a good question. All right, are we good with using our table to find a limit? So we can write out a table. We can use a table in our calculator, and we're interested in what our function is getting close to. All right, let's use a graph this time to find out what our limit is. So this time we're interested in the limit as x approaches 2 of x minus 2 over square root of x plus 2 minus x. So notice that f of 2, if I plug in 2 here in the denominator, I get 2 plus 2 is 4, square root of 4 is 2, minus 2, I get undefined. But this function does have a limit. So let's graph. So if I plug this into my y equals and look at the graph, I'm going to go back to my calculator for the y equals, clear that out, and I want the function x minus 2 divided by, and we're going to do the square root of x plus 2 minus x. And we'll graph that. Let's see, what did I do here? Standard, let me go to my y equals. Just want to make sure I entered everything in here correctly. Well, looks like it stopped there. Am I in radian mode? Yes, thank you. That shouldn't matter though, because I'm not. What? You got the same thing? All right. Zoom. Sorry, let me zoom out. Okay. Well, let's try this. What if I change this to a plus? Is this what I want to do? Graph. No?
You get it on the answer to as well.
Oh, there we go. So this is not the function that I wanted to graph. So this is my function's not graphing the way I was hoping that it would graph, and I'm not sure. Not sure what's happening here. So this isn't a good example. So let me think about this one some more, and we'll come back to this one in just a second. So if we're looking at a graph, the idea is that like we had on our last one. So let's just go back to our last example, just so we can look at this. So we have x squared minus 4, and we're dividing that by x minus 2. So this is just our same example, x minus 2, and we're going to graph this. And we saw that looked like a line, and if we were using our graph to estimate the limit, when we got to x equals 2, we could use our trace and look at our value here, and as x gets close to 2, we see that our function is getting close to 4. So that's how we would use our graph on our calculator to estimate our limit. So as x is getting close to 2, we see that our function is getting close to 4. And I'll think about that. I'm not sure where I made my mistake in that other function. Yes?
If you count x squared as negative, since it comes below negative 3, you count x squared as a negative.
Okay. All right. I'll adjust that one. We can take a look at that one a little later. All right. Questions on using a graph. Using a graph, just like using our table, we just look on either side of our function. If it has a function, we look at the function value, and that tells us about our limit. All right. All right. We can end up with functions with limits, and we just graphed one actually, limits that fail to exist, limits that do not exist. So there are several cases where our limits do not exist. So we have 3 cases where limits fail to exist. First case is our function approaches different values from the right and left. An example of this is the function f of x. If we look at the limit as x approaches 1 of the absolute value of x minus 1 over x minus 1. If we graph this, our graph looks like this. If x is greater than 1, f of x equals 1. If x is less than 1, f of x equals negative 1. So as I come from the right-hand side, the function stays right at 1. As I come from the left-hand side, this function stays at negative 1. So as I get closer and closer to 1, the function is not approaching one value. It's approaching different values from either side. So it stays really, really close to 1, and then boom, suddenly it drops to negative 1. So we can't say that the function approaches one value as x approaches 1. So this would be one example when the limit fails to exist, when our function approaches different values from the right and from the left. Our second case of when limits fail to exist is when f of x is unbounded. And the other way we say unbounded is increases without bound or decreases without bound, becomes arbitrarily large or arbitrarily small. An example of that would be the limit as x approaches 0 of 1 over x squared. If I graph this function looks like this. So as x approaches 0, f gets really, 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 really big. And the closer I get to 0, the bigger f gets. So we say f is unbounded. It's not approaching a single number. So we say the limit does not exist. And we're going to say the limit does not exist for all of these. And then our third case is when f oscillates. And an example of this would be the limit as x approaches 0 of cosine of 1 over x. And as x approaches 0, the graph of this function, kind of an interesting graph, it looks like this, and then it just gets all these oscillations in here, and then it looks, then it will come down like so, like this. So as x gets really, really close to 0, it oscillates back and forth, back and forth, back and forth, between positive and negative 1. So the function does not approach a single value. It's bouncing up and down between positive and negative 1 really, 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 really quickly. So we say in this case, the limit does not exist because it's oscillating between positive and negative 1. And as you go further in calculus, you'll talk about these unbounded limits. There'll be another way that you talk about them and the way you use them. But for now, we'll just say the limit doesn't exist. All right, questions on our conditions when our limits don't exist? So the bottom line with our limits is the function needs to approach a single value, a single fixed value, not bouncing around and not something that's really, really large or really, really small in order for the limit to exist. All right, so when we have nice functions, we can figure out our limits just by plugging in our number into our function when it's behaving nicely. So when it's not going to do one of these strange things, we're not going to end up dividing by 0. So let's talk about when we can do that and operations that we can do with our limits. So our properties of limits. Some of our really nice limits, our simplest limits. The limit of a constant is a constant. So b is just a number. So the limit as x approaches b of b is not changing. No matter what x does, b doesn't change. So our limit is b. Our second property, the limit as x approaches c of x is just c. So as x approaches c, x is getting closer and closer to c. That's what this is called. Yep. As x approaches c. So b doesn't change no matter what x does, b doesn't change. So the limit is just going to be b. We have a power of x. The limit as x approaches c of x to the n is c to the n. And the limit of a root of n, which is just a fractional power of n, or of x, is the nth root of c. So these are our nicest functions. The constant function, the function x, and powers of x. Those are really nice functions because we can find their limits just by plugging in c for x. Now what we're going to do is talk about how we can combine limits of functions, and then we'll figure out a nice family of functions that we can figure out our limits just by plugging in. All right, are we good so far? All right, let's talk about how we can combine limits. So operations with limits. So we don't always have nice easy functions like x or x to the n. We have more complicated functions, so we want to figure out how we can combine limits. So our limit as x approaches c of some constant times f of x is just that constant times the limit. So if we have a constant, we can just pull that out front. The limit of sums or differences. Is just the sum or the difference of the limits. So if my function is made up of adding several functions together, I can take each function, the limit of each function separately, and add or subtract those. We can do the same thing with a product. The limit as x approaches c of f of x times g of x is just a product of the limits. And we can do the same thing with a quotient, as long as we're not dividing by 0. And we want our limit as x approaches c of g of x not equal to 0. We have a quotient, we can just take the limit of the quotient of the limits. And if we have a function raised to a power, our last operation, the limit as x approaches c of f of x to the n, we can just raise the limit to the n power. So what we can do now is we can talk about a family of nice functions that just let us plug in c for x to find our limits. So our easy, nice, friendly functions, our friendliest functions over here, x to the n, n to the root of n, and a constant function. Combine that with these sums and differences, and we can say for polynomials or rational functions, we can find the limit by plugging in c for x. So if we have the limit as x approaches c of some polynomial function, it's just p of c. So if I have some polynomial function p of c and the limit as x approaches c of a rational function p of x over q of x equals p of c over q of c, as long as q of c is not equal to 0. And we'll talk next time about what we do when q of c is 0. It turns out we already know how to do this with all the work we've done with rational functions. We'll just put it in slightly different context. So polynomials and rational functions are our friendliest family of functions when it comes to limits. All we have to do to find our limit is plug in our x equals c to find the limit, as long as we're not dividing by 0. So let's look at a couple of examples. So the limit as x approaches 1 of 2x squared plus 6x plus 5. This is a polynomial. So all I need to do is plug in x equals 1. So that's going to be 2 times 1 squared plus 6 times 1 plus 5. And when I calculate that all out, let's see, I get 2 plus 6 is 8 plus 5 is 13. And if I have a rational function, x squared minus x minus 1 over x squared plus 2. All I need to do is check to make sure that when I plug in x equals 2, I'm not dividing by 0. Looks good. We have a polynomial in the numerator, polynomial in the denominator. So to find my limit, I just plug in 2, so I get 2 squared minus 2 minus 1 over 2 squared plus 2, and I get 1/6. So, limit, we're interested in what our function is getting close to. The function value is independent of the limit. But for nice functions, our function value and our limit turn out to be the same. And those are those are nice functions in other ways because we give a special name to the functions where their limit and their function value are the same, and they make it easy to work with. All right, questions on our introduction to limits. All right, so what we're going to do next time is talk about when we have functions that aren't nice, like polynomials and rational functions where the denominator is not 0. How do we figure out what kind of things can we do to these functions to figure out what the limit is? What is f approaching? What is our function getting close to? All right. All right, there we go.